Hi guys, today we're going to talk about a few examples of discrete random variables. I don't usually like to start with this much written on the board, but in the interest of time today, I'm going to go ahead and start this way. So let me begin over here. The first example of a discrete random variable that most people look at is a Bernoulli random variable with parameter p. So here this is a number p between 0 and 1. And what it represents is if we run one trial, p is the probability that that trial is a success. So for example, if you flip a coin, maybe getting a heads is a success, or if you roll a die, maybe getting a 6 is a success, and not 6 is a failure, or something. And so, as I have written here in the green, x always represents the number of successful trials. In the Bernoulli case, we have one trial. So that trial succeeds with probability p, and it fails with probability 1 minus p. So it's probability p that we have one success, and 1 minus p is that we have 0 successes. And what is the expected value of a Bernoulli? So just computing using the formula for expected value, it's 1 times the probability x is 1 plus 0 times the probability x is 0, which in this case, p is the probability x is 1, so it's 1 times p, and then the 0 times anything is 0. So it's actually just p. And so for Bernoulli random variable, the expected value is just the success probability p. Now, we may want to run more than one trial. For example, you might flip a coin 3 times and wonder how many heads do you get. Or when you roll a die 3 times, how many 6s. Or for a more practical example, maybe you're testing out a medication. And so you want to run n trials, and each trial succeeds with probability p. So binomial, np, the parameters, n is a positive, it's a natural number. So it's how many trials you're going to run. And p is the success probability of a given trial. So we run n independent Bernoulli trials, and each one of them succeeds with probability p. You can't change the probabilities in different trials for a Bernoulli. So really, we could represent the Bernoulli trials as y1, y2, up to yn, and then x is just the sum of how many of them are successful. So you count to 1 if it's successful, 0 if it isn't, and then you just add up the number of successes. And so x is going to be a value between 0 and n. You could have had all of them fail, maybe 1 succeeded, 2 succeeded, or maybe all of them succeeded, or so on. But it's got to be some number between 0 and n. So what is the probability that x equals k? What's the probability, in particular, that we had k successful trials out over n trials? Well, we have k successes if k of the yi succeeded, so k of these are 1, and n minus k of them are 0. So in other words, n minus k of the trials failed, and k succeeded. An example of that would be maybe the first trial succeeds, the second trial succeeds, up to the kth succeeds. So the first case trials all succeeded, but then the last, k plus 1 down to n, everything else failed. Then we have exactly k successful trials, right? And x would equal k. But these are independent, and the probability that y1 is 1 is p, that y2 is 1 is p, and so on down to yk is 1 is p. So the probability that all of these succeed is p to the k. Right? And then the probability that the rest of these fail, well, each one fails with 1 minus p probability. And now then if there were k successes and n trials, there's n minus k trials left. So there's 1 minus p raised to the n minus k probability that the last n minus k trials failed. And so down here, we see that we get p to the k times 1 minus p to the n minus k. That's the probability that the first k succeed and the last n minus k fail. But we also have this n choose k over here. And why do we have that n choose k? Well, that's because it doesn't have to be the first k that succeed. So we can permute these in any order. In other words, we could choose any k trials to be the trials that succeed, and then the remaining n minus k are the trials that fail. And so there's n choose k ways to have k successful trials. And so this ends up being our formula. N choose k times p to the k times 1 minus p to the n minus k. So that's the formula for the binomial. Oh, and we should compute the expected value. So the expected value of x, I think maybe the easiest way to do this is substitute. It's the expected value of the sum from I equals 1 to n of yi. Right? Because these two things are equal, so I can just substitute. Now, use the linearity of expectation. Right? If we have a sum here, I can bring the expected value inside the sum. And the expected value of yi, since it has success probability p, it's going to have expected value p, because each yi is just a Bernoulli. So this is equal to the sum from I equals 1 to n of p. And all this sum means now is just p plus p plus p plus p n times. In other words, this is just n times p. So the expected number of successes out of n trials, if each succeeds with probability p, will just be n times p. So in other words, if you flip a coin 10 times, the number of heads you expect to see are 5, because each one succeeds with probability 1/2, and there's 10 trials, so 10 times a half gives us 5 expected heads. Okay, so that's Bernoulli and binomial. Now we want to suppose that we're also modeling something like maybe phone calls. So maybe they come at rate 2 per hour. So how could we say, how could we visualize like how many phone calls do we get in 1 hour? And maybe we have like the phone calls come at these times, so they could come at any time, and it's from 0 to 1. Well, what you could do is you could chop up this line and maybe make these 2 different trials. And every time there's a phone call in here, you count it as a success. So this would say that we have 2 phone calls. And here we could say that we have 1 phone call. Now, of course, these are both wrong. We have 3 phone calls. But that's because our trials aren't accurate enough. We need to take smaller intervals. So maybe I chop up the intervals even smaller. And so now I count 1, 1, 1, and 0. So my trials, there's a phone call here, a phone call, no phone call, and 1 phone call. So I get 3. So you count each trial as successful if there is a phone call, and unsuccessful if there's no phone call. And then if I kept chopping, it wouldn't matter beyond this point because I've already counted all the phone calls. But if I want it to be as accurate as possible, what we would have to do is continue chopping and chopping and chopping into smaller and smaller intervals. That's the only way we can make sure we got all the phone calls. Right? So if they're coming at a rate of 2 per hour in 1 hour, we should expect 2. So the expected value of x is 2. And this is equal to n times p. Right, so for example here, n equals 4, so p should equal, what, 1/2. There's a 1/2 chance that there's a phone call in each 15-minute interval. But here n equals 8, and so p is going to equal 1/4. There's a 1/4 chance that in each 15-minute interval, or no, well in each 1/8 of an hour, we get a phone call. So notice that the number of trials goes up as we chop up more and more intervals, but the probability goes down. And that their product is always fixed, it's 2. So let's try to model, or let's see what happens to the equation here. So what we want to do is find the probability that x equals k. How many trials, or how many successes are there in a time interval? And what we want to do is take the limit as n goes to infinity, and if lambda is the rate, what we're going to do is say that n times p equals lambda, or in other words, just dividing over p equals lambda over n. And so this is equal to the limit as n goes to infinity of n choose k times p to the k times 1 minus p to the n minus k, which is the limit as n goes to infinity of n factorial divided by k factorial times n minus k factorial. And now then p is lambda over n. So it's going to be lambda to the k over n to the k times 1 minus lambda over n to the n minus k. Okay, and once we're here, we're taking a limit as n goes to infinity, and p depended on n, but now that we've substituted in lambda over n for p, nothing depends on n here. So anywhere we see an n, we have to take a limit, but k and lambda are just fixed numbers. So we can pull out the lambda to the k over k factorial. So this equals lambda to the k over k factorial. we have the limit as n goes to infinity. And now what we're going to want to do is break up some of this stuff over here. So we have an n minus k factorial divided by n factorial, and everything cancels except for n times n minus 1, and so on down to n minus k plus 1. That's all we're left with these two pieces. And on the bottom here we have an n to the k, but we can just write that as n times n times times n. And here there are actually k terms on top, because we go from, you think of this as, what am I getting? Well, there's 0, 1 up to k minus 1. So 0 to k minus 1 gives us k terms, and then there's n times n times n k times here in the bottom. And then we have 1 minus lambda over n to the minus k, and then we have a 1 minus lambda over n to the n. So I just broke this up. So this is two things added together in the exponent, so they can be broken up into the product, just by rules of exponents. And now if we take the limit as n goes to infinity, notice that this n over n goes to 1. This n minus 1 over n, this whole thing goes to 1. And then, because k is fixed, every one of these terms just goes to 1. This will go to 1. And also, lambda is fixed here, so as n goes to infinity, this will tend to 0. And so we'll get 1 to the minus k, and k is fixed, so this will just be a 1. So all we're left with then, everything here is just going to 1, except for this piece here. So we end up with lambda to the k over k factorial times the limit as n goes to infinity of 1 minus lambda over n to the n. And maybe I'll justify this in class, but it turns out that this limit here actually is e to the minus lambda. So what I'm using is this rule. So the rule is the limit as n goes to infinity of 1 plus x over n to the n is always just equal to e to the x. And so what I've got is a negative lambda in place of x, and so it becomes e to the minus lambda. And this is called a Poisson random variable. So the probability that x equals k, if we take this accuracy out to infinity, if we make that idea in the last that I had just a few minutes ago with the phone calls as accurate as possible by chopping up the intervals forever, we end up with x is Poisson with parameter lambda, and the probability that x equals k is lambda to the k over k factorial e to the minus lambda, where k is either, it could be 0, maybe there's no successes, or it's a natural number. Right, so you could have had 10 successes, 100 successes. There's no bound. It could be 1,000,000 successes, since we've chopped it up an infinite number of times. But it's got to be some whole number of successes. It can't be that you got 3 halves or something. So it's okay, some whole number is how many successes there were. So you can think of it as how many phone calls there are in an interval of time, or how many customers show up in the line in an interval of time, or something like that. So yeah, those are the 3 random variables we're going to study next time. Alright, God bless you guys, and I'll see you soon.